And so we're going to take a look at area, different types of area calculations that can be performed. Area by triangles, area by double meridian distance, or commonly known as DMD. Area by coordinates, area along an irregular boundary, and area of circular boundaries. So we have very simple triangle equations that probably most of you know. For a right triangle, 1/2 base times the height. But any triangle is very useful is 1/2 AB sine C. So that's the angle between the two included sides. That's a wonderful equation. And the other one is where you have all sides given with no angles. What you have is you have S as a perimeter value. That's half of the perimeter. So you take the three sides A, B, C, you add them together, divide by 2, and then you plug them into that equation, and that also yields you a value of area. Okay, so we're going to assume we have a triangle with sides of 32, 46, and 68 feet, A, B, and C. So the first thing we would do is calculate that perimeter sum, half of it. So we just take the values 32, 46, 68 divided by 2. That becomes that constant S. And then we just plug that in. S times the S minus A, S minus B, S minus C. Just do that. And what you'll come up with, this will be in whatever square unit you're in. So that we started out in feet. That gives us 635.65 square feet. So the second problem is dealing where we have the very simple process where we have two sides that are known and an included angle. So in this case we have the two sides with the included angle. And I calculated this, but we didn't actually need it for this problem, which is nice. So we're just calling that arbitrarily A and B, and that's your included angle C. So we just 1/2 AB sine of C yields you that solution very nicely. Okay. And we have a right triangle, of course, which is 1/2 AB, or base times the height. And that's only going to work if you have a 90-degree angle. Okay. So area by double meridian distance is the case where you have adjusted latitudes and departures. So it's a pretty slick little method of doing it, but it's just got a little bit of a setup. But again, it does use adjusted latitudes and departures, quickly compute area. DMD will set up a series of triangles, or trapezoids, excuse me. Actually, some could be triangles inside or outside of your boundary. And some trapezoids will be negative, some will be positive. When you add the sum of those together, what you'll get is the yielding the area of the parcel. So it uses, again, both the departure, which is actually your meridian distance. That's the distance from the meridian to the midpoint of the course. And then you're going to multiply that by your latitude. So you're actually getting double the distance, and that's why this is called double meridian distance, and at the end you're going to divide this by 2. So double meridian distance has a couple of rules. It's pretty easy to follow. The first rule is that when you're calculating, the first DMD is equal to the first departure of the first course. Then each succeeding course DMD is equal to the DMD of the preceding course plus the departure of the preceding course plus the departure of the course itself. And you're going to do that through the whole process until you get to the end, and the last course should equal the departure of the last course, but it should have an algebraic sign opposite. So if it doesn't have the opposite algebraic sign, or it doesn't have the value being the same, then you did something wrong. All right, so the area is found by first getting your DMD values of each course, and you're going to multiply those by your latitudes for each course. And you have to consider the algebraic sign. So if you have a negative latitude and a negative DMD, then you're going to get a positive value for your what's called double area. And once you get that, you're going to add those double areas together algebraically and divide that by 2, and that'll be your total area at the end. Okay, so here's an example. What we have is given adjusted latitudes and departures. So notice if you sum this column up, you should notice that these go to zeros. Okay, both. So what we're going to do is now calculate the DMDs. So this is the way this works. Again, So you start out by, a lot of authors like to say start at the most westwardly point, and then you don't have to worry about having negative DMDs. I think that's a waste of time personally. Just start where you are and just follow the rules. So what you're going to do is the first DMD is equal to the first departure, so we just take that, write it right here. And then each succeeding DMD is going to be equal to the DMD of the preceding side plus the departure of the preceding side plus the departure of the side itself. So we're simply taking this, and we're writing that answer here. So we do the same thing, DMD of the preceding side plus the departure of the preceding side plus the departure of the side itself. Again, we're following the algebraic signs. We write this here. We do this for each course until we get to the end here. And notice when we get to the end, if we've done this correctly, this is going to be the same magnitude but opposite sign. So that's your key that you've done it correctly. So whether you have negative or positive DMDs, you can have negative or positive. It doesn't matter, just so long as you're following the rules. So then to get the areas, which we call the double area, you're simply taking your latitude times your DMD and getting that. So notice, again, you've got to follow your signs. Negative, positive gives me this. Negative, negative gives me positive. Double area. So your double areas can get rather large. Okay, that's the only downside to this. But you just follow that rules. When you get done then, you're just going to sum this column. And when you sum that column, that's your double area. So after we've gone through, which we did on the other pitch showing, this was the DMD column, and notice I always check that, make sure that's good. I've calculated my double areas. So I'm going to sum these algebraically. It gives me that number here. Again, you remember you have to divide that by 2 because that's your actual answer. And so if you converted that to acres, we would have 5.672 acres. Okay, so the other method we've already talked about was the area by coordinates formula. So again, you can just take your northings on one side, eastings on the other. It truly doesn't matter which way you go with that, just so long as you're doing that. Now keep in mind the key thing I said before, if you start with A, you must end with A. Okay, so again, 3 sides here, we're going to have 4 total values. So we just multiply across, that cross multiplication, and we consider going the one direction. So I'm going this way, A to B, I'm considering that positive. B to C, positive. C to A, positive. Then we're going this way, negative, negative, negative. Now, if you have negative coordinates in there, you have to consider that. So you really don't ever want to deal with negative coordinates. Everything should be positive, then this comes out to a lot better process. But once you sum those products up algebraically, you're going to divide that by 2 to get the actual area. Again, you can have a negative answer there, which doesn't indicate a mistake. It just indicates the way you went around the figure. So one of the things you can do to simplify your work when you are given coordinates, so notice the coordinates that are given on the left side there, northing and easting, they're rather large. They're all positive values, which is great. But if we can translate this, if we can move this figure to a westerly point and a southerly point, what we can do is we can get zeros. So translating is very easy. I just look at what my smallest northing value is, and you notice my smallest northing is looks like 0.5. So I subtract that number from all of the values of the northings. What that does is that gets that one to 0. So when I do negatives, or when I do my multiplication, I drop some of these things out. So it makes these numbers smaller. So again, I subtracted that 574.45 from each one of these to translate it into the north, but I got a 0. I did the same thing with the east, and I got that, I looked at my smallest easting value, and I get 248.31. I subtract those all from that same number, and what I end up with in this translated figure with those 2 zeros makes a huge difference when I go through and do this calculation. So this is the same picture, same coordinates that were given. I translated it here. So notice what I've done is I have taken and started, there's 1, 2, 3, 4, 5, but then since I have 5, I have to put this one down here. So always, whatever you start with, you end with on both your northings and your eastings, and then you just start doing your multiplication. So down here, I'm taking this guy times this, gives me this value here. Notice there's my 1, I just dropped 1 out right here. There's my 0, and I've got this guy, you can see that. So I have 1, 2, 3, 4, 5 sides. I should have 1, 2, 3, 4, 5 products positive. So I'm going to go the other way, this way. This is going to be negative, 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 and negative. I'm missing an arrow there. So again, negative, negative. Notice the 2 zeros in there, which have lessened my sides or my values. And then when I get done, I'm going to add the sum of the positive ones and the sum of the negative ones together. I get an ultimate answer there, which I have to divide by 2 again, get my square feet, and notice this actually happens to be the same parcel we looked at before, but we get the 5.672 acres. Okay, so another problem you might be hit with is an irregular boundary problem. So this is a case where a tract of land is bordered by things such as a stream or a lake or river course, something like that. So you can establish the area between the irregular boundary and what we call a baseline. And you divide that baseline into equal segments that form trapezoids or triangles. And so this irregular boundary can then be calculated using either what's called the trapezoid rule or Simpson's 1/3 rule. We're going to take a look at trapezoid rule. You can look up Simpson's pretty easily. I really doubt they would probably hit you with something like that. I think trapezoid would be the more common method that you'd be looking at. So what we do is the trapezoid rule assumes that your irregular boundary is going to be made up of a series of straight lines. So we're approximating that irregular boundary. If the distance is small enough between the trapezoids, then it approximates it much better. So they're kind of a point of diminishing return if you were doing this in the real world, but that's kind of how you could do it. So we will make a small base distance, maybe 25 feet, 55 feet, and then you're going to run what are called tie lines from that baseline perpendicular out to where it hits your curved boundary. So again, the smaller the number base, less significant the areas. The trapezoid rule does require that your base distances are constant throughout, so that's the one thing that's important about it. So this is the trapezoid rule. It basically says that your area is equal to your base distance. That would be your little value of 25 feet or 55 feet. We'll show you here an example. And your tie distances that are measured perpendicular to that out, you might think of that h as the height of your trapezoid. So your first one, you're taking and dividing it by 2, then your second one is full value, third is full value, up and up and up until you get to your last nth value. So you can do this for any number, odd or even, and you divide that by 2. Okay? Now if you are using Simpson's 1/3, that can only be used with an odd number of offsets, so it would never be with an even. But trapezoid can go, you can have 10 sides or 11 sides, it doesn't matter. So this is a graphic depiction of the trapezoid rule, and it's just kind of generically showing you. So this would be your first side, second, third, fourth, fifth. This would be the nth, or in this case the fifth. So notice this is your baseline B. So this is B distance, B distance, B distance. So these are considered your ties. So that's kind of how that works. So this is an example of an irregular problem. This would be something you might actually see on one of those tests. So notice they're giving you the irregular boundary. Now we have a triangle here, so we're going to handle that separately. So the trapezoid rule is going to be applied from B over here to H, because this changes. Even though that's a trapezoid, that 35 feet is no longer part of the B distance. So we're going to handle that as a separate trapezoid, and then we're going to handle that as a separate triangle. So the triangle, this is just a 1/2 AB kind of thing, base times the height, so we get that. So the trapezoid rule is going from B to H. So notice the B value is 50. The first one we're dividing it by 2, then we're adding that one full blown, that one full blown, that one full blown, that one, and that one, until we get to this last one. We divide it by 2. So we do that sum, multiply it by 50, and we come up with the number of square feet in that section. So then the HJ trapezoid, we have to do that separate. So that's just the 2 sides added together divided by 2. So the average height times the base on that one gives you this. And ultimately, again, we have another right triangle, 1/2 base times the height gives me that. So the sum of all of these guys go together, and this would be your total. Well, I could see that this would be a typical type of problem. Okay, circular boundaries are another thing. Everything we've looked at so far is only going to get approximated or give you straight lines. So if you have circular boundaries, which are going to occur along highways, streets, railroads, you're going to have to deal with them. So what you can do is calculate the circular boundaries separate using some kind of arc calculation, and then some combination of all those other straight lines that we talked about would be a way of doing that. So formulas can be derived for either what's called a segment or a sector of an arc using the central angle and the radius. So those are going to be the two key things that you're going to be given. So a segment is kind of like a slice of pie, if you will. Look at that. So basically, a circle is 2r pi r squared. So what we're doing is, for a full circle, that would be 360 divided by 360 times pi r squared. But what you're saying is a delta is a percentage of that. So if you had a 30 degree slice, would be 30 divided by 360 times that. So it's just giving you a percentage. So a sector would be the area that is bounded between the arc and the long chord. And so basically what you're doing is you're calculating the segment of a circle first, and you're calculating out of that, or you're subtracting out of that the triangle piece that is existing below the chord, and you wind up with the equation r squared is equal to the pi delta over 360 minus sine delta over 2. Okay. So here's your segment. Again, the slice of pie, the crosshatched area is what you're going to get. You know your radius, you know your delta. This is what you're getting here. Your sector is your chord and your arc. The crosshatched area is what this equation will yield for you. Your segment minus the area of the triangle. Here's your triangle right here. And this is basically a 1/2 AB sine C. That's where that's coming from. So a couple of examples that we would have. So if you're looking for the sector itself, I've got area of the segment minus area of the triangle. Here's your area of your segment. Here's your area of your triangle. And what you're doing is you can factor out the r squareds, and it comes up to that. So that's an easy way of looking at that. So let's look at a simple problem here. If we wanted to calculate the segment of this versus the sector, I've got a bearing coming in on my curve. I've got a bearing going out. The difference between those two bearings in this case, because they are in the same quadrant, is going to yield for me my delta angle. So knowing a given radius of 500 and a delta angle, the segment, so that would be this piece right in here, it would be pi r squared times the percentage of the pi to the 360, gives me an area there of 175,335, and that of course would be square feet. If we're looking for the segment here, the sector, excuse me, this piece right here would be the long chord. This would be the area, so we'd just be getting that little piece. And so we can see we just plug it in. So there's quite a bit of a difference in the terms of those areas. So if you were doing a problem of this nature, you may have to solve this like through D&D, something like this, maybe through D&D, and then you can add either the segment or the sector into it, however you